Hello everyone, my name is Eunchan. I am a senior in Ethiopia, and my project was about prosthetic hands kinetic movement and force closure grasping analysis. And this is basically a project that I did for my community here in Addis Ababa, Ethiopia. So prosthetic hands are mechanical hands that are made for amputee patients in Ethiopia. Especially in Ethiopia, there's around 43,000 amputee patients, especially because there's internal war going on between Tigray and Amhara. So right now, since 2022, there has been ongoing conflict and military clashes between the government and the specific ethnic groups that are living in the northern area. And because of this, of course, we're going to see a lot of amputee patients due to this war. A few weeks ago, I had a patient who blew up his index finger because of a grenade. So we see that in Africa, there's a lot of cases where a lot of people are either suffering with limb losses or limb pain. So this led to my project of thinking of helping how we could actually support these amputee patients through a prosthetic hand. So prosthetic hand, actually I have one, looks like this. It works based on the mechanical force of your wrist. And based on that, we are able to actually move these fingers. And by doing this, we can help amputee patients to grab real life objects or use it in real life, shake hands, or just use it in their daily lives. But the problem is that we are not actually sure of how much force is the prosthetic hands are able to grasp on. So because of this, sometimes they may be having difficulties with holding objects like pencils or like bottles. And because the movement is really limited, we're also not able to know how much it's going to be helpful in the real life. So I wanted to explore more about this, especially on the grasp force. So how much force when they're grasping an object, they will be able to balance out the weight in the object and actually hold it. So this led to my project of working on prosthetic hands especially, and its application and the studies of grasp force analysis. So the way it works is that I first started with the random polyhedron. So Wolfram gives us this unique function of generating any random polyhedrons. And I really wanted to generalize the object into any shapes and any form. And this is why I started exploring these random polyhedrons. So the way I started was that I first find the random contact points. And based on that, I'm able to find the normal vectors from that surface. So over here, we see the small triangles, we hold the small ashes, and we can select a random ash and find its normal vector, its contact point in a 3D space. Based on that, I was able to find the contact points. And meanwhile, while I was working on this, I also worked on kinetic movements because, as we know, we first have to know the movements of his fingers when we're trying to grasp an object, and also consider the clasp, the angles here between the joints, because of course, no fingers is going to move backwards or with like 270 degrees. So because of this, I was working on both forward and inverse kinematics. So forward kinematics was used for basically a demonstration that I used that was posted, but also uploaded in Wolfram demonstration repository as well. But this one is about how the fingers move. So when we're considering the endpoints here, when we're moving this, we have to both consider the joints. That's the MCP and DIP here. And because of this, we have to consider their angles and also their length and their displacement. And then, of course, all these should be combined together. So this is what I use for my forward kinematics. It is pretty much intuitive. So we're considering the length and angle of how each segments of the finger are moving. So this was used for animation and also reaching out to the contact points and see like when the hand is moving, at which point it would meet the contact points. And after that, I also worked on fabric. So fabric is a form of inverse kinematics. This is where it was used to actually find the first contact points and making the fingers go to that contact points. So this is more of inverse kinematics. And what I used was, first of all, using forward reach to make the angle, the finger segments go to the point and adjust it, and do this iteratively a lot of times, which means that at the end, the algorithm will be able to find the perfect length and the vector to that point. So this is how it looks like in formula, and this is what I was using it for the final product of where there are several points on the random polyhedron, and the hand would go, the tip points of the fingers would go to that point. And combining this all together, I was able to come up with grasp force. So grasp force is a concept that is used in robotics. So it's basically trying to see how much can we grasp an object, how much force is needed for that, and can we actually weight out the gravity of it? Because the whole point of grasp force is that we're able to lift up and grab objects mid-air and able to balance out the weight of that object. So what I first started was that I started with I found the contact points first. Of course, there's 5 contact points, and then we are able to find the tangential pair. So at each point, there's going to be a force acting upon it and also a torque working upon it based on the center of the object, the center of mass of the object. So based on that, I was able to find the vectors, so the 3D XYZ vector of the force and torque, and of course the normals. And based on that, I was able to end up with a 6x3 grasp map. The reason why I used it by 3 is that the last one is about deformation, but we're using PLA plastics. So I tried to condense it down to 6x3 matrix that is shown here. And this basically shows the amount of force that's needed. So points, normals, and tangents all combined together, giving us a value. And based on this, if we compute this back again, I'm able to find the amount of force that's needed for each contact point. So the 3D vector force for each point. So based on that, I further worked on friction cones. So friction cones is also a concept that's used in robotics. It's used to show how much the range of force that is being computed. I did not have the image yet, but it's somewhere down there. I couldn't find it, but it shows us about, for each point, how much range of force that can be applied that would still lift an object up in the air. So based on this, I was able to find the 5 contact points, the normals, and the force that should be acting upon it. However, we have to also consider that if we're using random polyhedrons, not all points are going to work because sometimes it computes some weird combinations of points. Because of that, I also created an iterative method where I would first find the points and find the grasp force if that would work. And if it doesn't work, it would search for a new contact points. And this didn't matter to 5 points, but sometimes it also works with 4 points or 3 finger points. And based on this, I was able to find the contact points in the polyhedron where grasp map could be created. And based on that, I was able to compute the inverse kinematics to move the hands back to those points where it worked. In the future, I really want to set this to a practical stage. So I'm creating these prosthetic hands right now, but I want to improve their functionality and also the amount of force that it could actually compute. So the way this works is that there's tension force acting upon the hands. So based on the grasp force, we're able to find how much force is needed. And by that, we will be able to also compute if this tension force is able to weight out, so cancel out that grasp force. And if it doesn't work out, I'm thinking of either changing the tension force or the angles here, because here it's connected to the IP here. So based on this, I'm thinking of how we could actually use this grasp force to allow patients to grasp objects and move them and weight out the gravity in mid-air, and use it for revolutionizing healthcare access in Ethiopia and Africa. Thank you so much.